what I'm about to talk about is simply this, that dz, dy, dx, that's how you integrate in 3D. And if you use cylindrical coordinate system, we already saw that this changes into r dr d theta. So it's r dz dr d theta. And I spoke about why you need this r by using some geometrical arguments. And then in spherical coordinate systems, you have d rho, d theta, d phi. And now the question is there something similar to r that you need? Well, one thing that we do know for sure is that because these are angles and this is a length, this has the dimension of just length to the first power. Remember that angles don't have any units in the physical units. That's because when you have the arc, if you have a radius r circle with this to be the arc length, then theta is defined as simply arc length divided by the radius. That's the way you define radians, and because the ratio of two lengths, the unit is 0, and it doesn't have any unit in the length. So since these are unitless in terms of lengths, you need length squared here. So your first thought might be, oh, should we do rho squared? Because that's the one that has length here, right? But it turns out that you need one more, which is that you need sine phi. Now you could argue this geometrically somehow that, see, if this is the rho direction, then d rho will be the small increment there. And the small slice that we're looking at is like, we look at the, see, this is, so theta turns things around, right? So d theta would be over here, turning, and then d phi would be the amount that's coming down. So this angle here, this will be d phi. This will be d theta. You're opening d theta. Here's the z-axis, and to get the volume of this small parcel of volume, this length here would be d phi times rho. So you need this length to be rho times d phi. Okay? And then this length here really depends on the r. So this right here is r times d theta. And if you use that the volume is base times length times width times height, then you have dv equals to rho, no, d rho, which is this length, d rho times rho times d phi times r times d theta. But then r is what? R is rho times sine phi, right? That was the formula that we had before. So you do that and you get exactly this formula if you do that. If you use r equals to rho times sine phi, you get that answer. However, I want to show you a more mathematically rigorous thing that works for any kind of transformation. So what's happening is that you're going from one variable to another, right? If you go from one variable to another, there's some kind of thing that you have to multiply, which is known as the Jacobian. And that Jacobian has to be calculated and multiplied. So let me go back to the polar coordinate system and try to give you another reason why we have r. So if you go from dx dy to dr d theta, what you need is you need something like, it's just like, you know, dy, if dy is equal to dy over dx times dx. This is what you use in integral calculus, right? So for example, if you have u equals to x squared, what do you say? du is 2x times dx. That's what you use for u substitution, right? And what is this? This is really, you're taking u, which is x squared, and you're differentiating by x, right? So if you replace this by that, you have a identity that makes a lot of sense just by looking at it. See, these two cancel and then you get the same thing, right? So this is another implementation of the chain rule. Like, you can think of it in different ways, but this is what we really had in one variable. And there's something similar in multivariable, which is known as the Jacobian. And the way you write is you put x comma y here, and then you put r theta here. And the thing that you have to be careful is that because this is the conversion of area, sometimes you have to take absolute values to make sure that it doesn't become negative. Okay. So let's think about what that is. We know that x is equal to r cosine theta, and y is equal to r sine theta, right? Okay. And the dependence diagram goes like this. X is a function of both r and theta. Do you agree? Y is also a function of both r and theta. Right? So what you can do is you can take the x and differentiate by r. You can take x and differentiate by theta. You can take y and differentiate by r. You can take y and differentiate by theta. You have 4 different possible partial derivatives. Okay? And what you need to do is you write them all, but if you have 4 different ones like that, you can write them as a matrix, right? A matrix is not a number. How do you get a single number out of a matrix? No. Determinant. You take the determinant of that, okay? So that's what you do. So what you do is you write down partial x with respect to r, partial with respect to x with respect to theta, partial y with respect to r, partial y with respect to theta. You make this as a matrix and you take the determinant. That's what goes in here. Let's see what that is. Okay, if you differentiate this by r, what do you get? It's a partial derivative, so you're thinking of theta as constant. So cosine theta will be constant, right? What do you get?
1/2 r squared.
No, that would be the integral.
Oh.
If you're differentiating, yeah, what do you get?
Oh, just cosine.
Cosine theta. How about this one? If you differentiate this by theta. Cosine differentiates to?
Negative sine.
Negative sine. Okay, negative r sine theta. Okay, if you differentiate this by r, what do you get? Differentiate this by r.
Sine theta.
Yeah, just sine theta. Okay, if you differentiate this by theta, what do you get? R cosine theta. Do you know how to do determinant? AD minus BC, right? So you multiply these two, you get R cosine squared theta minus negative R sine squared theta. Oh, that's R cosine squared theta plus R sine squared theta. What's sine squared plus cosine squared?
1.
1. So if you factor the R out, you get R times 1, which is just R. That's what that is. Now, you might wonder, why does determinant play a role here? Well, because what is the determinant? It's the area of the transformation. Did we do this? I'm not sure. So if you have t of x comma y to be ax plus by cx plus dy, then you can think of t of xy as a, b, c, d of xy, right? If you do across down, you get that. Across down, you get that, right? And then the meaning of the determinant of a, b, c, d gives you the change of area from one to the other. Did we go over that? Did we talk about that? Determinant having the area.
Oh wow, you're right.
Yeah, I think we did talk about it, but in case you forgot, well, such a thing is called a linear transformation, and what happens is that, let's say you have t, x, y, like 2x, 2y. What's that? That's in matrix form, that's 2, 0, 0, 2, x, y, right? That's what it is, right? But what does this do? It takes a small shape, any region R, you apply t to it, then it just becomes bigger, right? Yeah. T applied to region R will just make everything twice as big, right? Yeah. But if that happens, what happens to the area? Area becomes how many times? If all the lengths are doubled, then the area becomes? Okay, question. Twice, 4 times, 8 times, 16 times. Which one? 4 times. If the lengths double, then the area becomes quadrupled, right? So if you take the determinant of this, that's exactly 4, right? 2 times 2. And that's the meaning of the determinant. If you think about these type of transformation, say if you have x and y mixed, then it will like rotate. Sometimes it might squeeze. So you have like all kinds of linear operations that you can do in the plane. And anytime you take the determinant of the matrix form, you end up with how much the area transforms. So that's why here there's a determinant. So if you go from dx dy to dr d theta, of course you will need some kind of a derivative like this in the spirit of the one-dimensional calculus, right? In the one-dimensional calculus, it was simple, but now you have several things to differentiate by. So you just write down all the possible derivatives, right? But then after this, in order to really convert this into how much the area transforms. So without the determinant, the original thing sometimes is also called Jacobian, but sometimes it's called the derivative of the transformation. You take that derivative of the transformation, and if you want to extract the information about how the area transforms, then you have to take the determinant, just because of this is what determinant does. Okay, so that's the vague idea. I could spend a lot more time doing this, but then I might take like 1 week trying to explain what determinant is. Then once you fully understand what that is, then we can talk about what the derivative is, without the determinant, and then we tie those together. It'll probably take 2 weeks. Not usually done in a calculus class, so this is as far as I'm going to go. Yeah. But it kind of makes sense, right? Good? All right. So now, the next question is, what would happen if we did the same exact thing in terms of the spherical coordinate system? Now, uh, you could go from dx, dy, dz to d rho d theta d phi and put this gigantic one here. Um, but that's going to be pretty painful because now you have to do x, y, z. Remember, z was rho cosine phi, and x and y were rho sine phi, but this is really r, so it's r cosine theta, r sine theta. So you have this huge thing, and you have to make this, and it's going to be 3 by 3 matrix because you have to differentiate this by r theta phi, r theta phi, r theta phi. And by the way, if you differentiate this by theta, you're going to get 0. So this is like, if you really want to know what's going on, this is a nice thing to try on your own, okay? Which is you will have a gigantic 3 by 3 matrix, and if you take the determinant of that, you'll get exactly rho squared 9 phi. Okay? Now, but for us, let's take a shortcut instead of going this way, because we've already accepted that dx, dy, dz equals to r dz dr d phi. We just want to go from here to no, d theta, sorry, d theta. We just want to go from here to something d phi d theta d rho d theta d phi. But here's the thing: d theta are the same anyways, right? So what we're going to do is we're just going to say that we're going to keep the r, but rewrite r. R is rho sine phi, that's already there, okay? Rho sine phi. And we're just going to take the d phi and don't care about that. D theta, I keep reading it wrong. So take the d theta, don't care about that because that's the same. But we're going to go from dz dr to d rho d phi. You get that? dz dr to d rho d phi. So we're going to do z comma r and rho phi, and then d rho d phi. Okay. And if we get this as rho, then we are done, because then you get rho squared sine phi, which is what's to be proved. Okay, so let's try that out. Okay, this is a good time to review the formulas for the spherical coordinate system, not by memorizing them. I told you to remember this picture, right? So the picture is that if you come down from the North Pole, that's the phi, okay? And when it hits, of course, this length is z and that's rho, but then you have to realize that this length is the same length as what we call as r in the cylindrical coordinate system. And from here, we can get the relationship between r, z, and phi rho, which is z is equal to rho cosine phi, and then r is equal to rho sine phi. Okay, so that makes it easy. Now you can just write down all the possible derivatives. So you differentiate this by rho, differentiate this by phi, differentiate r by rho, differentiate r by phi, and take the determinant. Let's see what happens. And this is essentially the same exact calculation as we've done before. You can recognize that, right? So if you differentiate this by rho, you get cosine phi. If you differentiate this by phi, it's rho, negative rho sine phi. You get sine phi here, and then positive rho cosine phi. So this is essentially the same calculation that I did a moment ago. This becomes cosine squared plus sine squared, which is 1, and rho is multiplied, so you get a rho. So that becomes rho, and then if I replace that by rho, I have rho sine phi times rho d theta d phi, and then this one, rho times rho is rho squared, so finally you have this as what I was explaining in terms of geometry, okay? So you can gain some more confidence with this. So at the end of the day, what I'm really trying to say is that whenever you convert from the rectangular coordinate system to a spherical coordinate system, you need to have some factor that would fix the changes in the coordinate system. For the cylindrical, it was r, but for the spherical, this is rho squared sine phi. This is really important, okay? So I'll show you how to do calculations using this next time.